Okay, so we are now in the section of exponential growth and decay. So we yesterday have the example of what is exponential growth. And here's what we call an exponential decay. So what is exponential decay? So the law of exponential decay says that say decay is usually related to problem of radioactive decay or something. So say this is radioactive decay. It says that the amount of the growth, decay rate of radioactive material is proportional to the amount of the material at that time. Okay. So what it says that so suppose the Y is the amount of material, radioactive, at time t. So this says that dy over dt is proportional to y of t. Okay, so let's say if we replace this proportional sign, that would be dy dt equals k for some constant k. We need to find out that constant. Okay, so this is what you call the radioactive law of radioactive decay. Okay. All right. So this is an example here. Carbon-14 is an isotope of carbon. It is radioactive and decays at a rate proportional to the amount of the present. Okay. Its half-life. All right. So this term half-life is 5,730 years. See, so it takes that many years for the material to decay half of the original amount. Okay, so that's the data. If there were 10 grams resin originally, how much would left after 2,000 years? All right, so let's do this one. So suppose Y is the material here. So we have the differential equations. So let's find out the K and D. Okay, so in this case would be, let's see, dy over dt equals k times y. So if you move to the left hand side and k dt, so this is separable. You separate y and t, you get ln of y and integrate, right? So ln of y. So this is kt plus c. Okay. But y is positive, right? The amount is positive. So is that's equal. Okay. So then when you take raise to the exponential, right? So raise to the exponential will cancel the ln, so you get y only, e to the kt plus 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 c here. So this e to the c, e to the kt. So we write this down as there. Okay. And c tilde is constant that we need to find out. Okay, so we have two constant need to find out. Okay. All right. So what it says, its half-life is 5,730. Okay. The original size. All right. So that. Okay. Well, first, we need to recognize what C is. What is C? All right. So if we plug in y0, this is means times 0, the initial data. 0, you get that e to the 0, that's in C. All right. So it turns out to be that's the original, the initial amount. So this tells you that C is initial amount. Okay. So from here you can we know that the formula should be KT. So we know that. Okay, so half-life is 5,730 years. That means if you plug in that 5,730, you get equals 1/2 of the okay, so that means half-life. So the amount is half of the original, of the initial. Means half of the initial amount. Okay. And so we solve this one for k. Okay. So how we solve this? First, you can cancel the e to the equal to 1/2. Cancel this one. So it's 1/2. So that means if you apply ln and that cancel the exponential, uh, 1/2. Okay, so that's negative ln of 2, right? Because 1/2 is, so let's go backward one step. ln 2 to the negative 1, right? So this way we can factor the negative 1 out. So there you go. Okay, so you know that k is negative ln of 2 divided by 5370. All right, so that's the K. So now the equations, the amount of the at any time, you can write this down as why not, right? So this initial amount, e to the negative t out of 2, 5, 3, 7. Sorry. Oh, sorry. 5,730. All right, so that's the thing. Right? Okay, so we know the formula now, and then we can answer the last thing it asks. If there are 10 grams present originally, so this is the Y naught initial amount. How much would be left after 2,000 years? Okay. So the question is 10 grams. Then Y of 2,000, so it is in years, is 10, all right? E to the T is 2,000, negative 2,000, ln of 2 divided by. Now I would like you to compute this number. Use your calculator. What you get here? Not to be exact, but at least. Okay, anyone get the number? What's the number should be?
I got 7.85, sir.
7.8. Thank you. That's whatever. Okay. So this is the amount after 2,000 years. So it takes long time, right? Okay. Okay, that makes sense because the half-life is 5,000 years something. Okay, and 2,000 is not even half of this the half-life. So it's more than more than 5. 5 is 1/2 of 10. Okay, should be around 1/2 of this those. Okay, so that makes sense. All right, so okay. That's what call uh, the exponential decay. Okay, one more example of this is, let's go to get to the book, what we call a Newton's law of cooling. So I want to write this down. Okay, Newton's law of cooling. Let's say so the rate of change of the all right. So you have some, say, some warm or hot object uh, in a room, right? Say room temperature. Okay. So it will cool off. Okay. So the warm object will release energy. So it will cool off. All right. So the rate of the change of the temperature of the object is proportional to the difference in temperature between the object and the surrounding media. Okay. So if you have T is the temperature, the capital T, so the rate of change is the T over dt, the uh, capital T. So proportional means K. So this difference is T minus T1. T1 is the surrounding temperature. There's the ambient, call it ambient temperature. Okay, so this is Newton's law of cooling. So let's solve a problem using uh, using law of cooling. So this is called ambient temperature. Of course, the assumption is that the room is large. It's a say large enough so that uh, the 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 cooling of the object won't heat up the room. Okay, so this is constant. Okay. So imagine if the room is small, really small, then of course the room will warm up. Okay, so this is not the case. Okay, let's pick a problem. Let's see the compound interest. Let's see. All right, so this is the right. So problem 23. Type of problems, the crime CSI type of problems. So this is the crime scene investigations, those kind of stuff. So a dead body is found at 10 p.m. Have temperature this. Okay. An hour later, temperature was down by 4 degrees, so 76 Fahrenheit. So the temperature of the room was constant, 70 degrees. Okay. Assuming temperature of the body was when it was alive, estimate time of death. Okay. So this is Newton's cooling law. So what it states as a temperature of, say, that body temperature is T time T. Okay. So by Newton's cooling law, just go directly with this. Okay. T minus the temperature difference. Okay. Temperature difference with the ambient temperature. So the temperature, the ambient is 70. Okay. So let's see. The temperature of the body was, this one is alive. Okay, so the time of the death, so this is the temperature. Okay, so you can say this is so I would say this more precisely. This Tt is the temperature of the body. T time after death. Okay. All right. So T0 is the time of death. Oh, is the time of death. Okay. Okay, so this is what we try to solve. Right. So let's try to solve this one. The T over T is a, okay. So let's remove the T minus 70 to the left-hand side. Right. So it's K T, sorry, K D T. So when you integrate, you get Ln of T minus 70 equals KT plus C again. Okay. So because the temperature of the body is always larger than the, higher than the ambient, uh, always warmer than the surrounding. The room, then T minus 70 is just T. Yeah. Okay, so we can get rid of the absolute value and take the exponential. So you get T minus 70 is, say this is C. Okay. So T is say this is 70 plus okay initial data. If you plug in T equals 0, this is just, see, this is 0, just 1, then equals 98.6. Is that true? Okay. Okay, so here we get that C prime, sorry, C tilde is minus 70. This is 28 times 6. Okay, so we know the equations now. That's 70 plus 28.6 e to the kt. All right, one more thing. We need to find this k. Okay, so how do we find this k? All right, so this is 1 hour later temperature. Okay, here's good. Okay. This is what we know. Dead body is found. Okay, so depends on the okay. So this is time 0. This is the time of the death. Okay. So this is 10 p.m. I don't know what time. This is the T. Okay. So at time say T0, so not T0, T1. Okay. It is found to be that's 10 p.m. T1. That is 82. Okay. So they say that T of T1 is 82. We need to find out this T1. Okay. And 1 hour later, the temperature of the room was a constant. Let's see. Temperature was 76. 1 hour later. Okay, so this tells you T of T1 plus 1 is 76. Okay, so we try to find the data from here. Okay, so the data T of T1 is 1 hour later. T1 is 76. Yeah. Right. Okay, so just substitute this data. Okay, and you do substitutions. It's 70 plus 28.6 e to the kt1 is 82. Okay, so we'll try to find the k and t1 and another data is 70 plus 28.6 e to the k e1 plus 1 is let's say 76. From here we need to find k and t1. This is the question actually about what's t1. Okay. Because t1 is this is at 10 o'clock, right? 10 p.m. So T1, the time of death is so 10 p.m. minus the T1. Okay, so we need to find this out. All right, so let's compute this. From here, we get 28e to the T1 is 12, right? So e to the kt1 is there. Go. So from here, K T1 is, let's see, Ln. There. Okay. And from here, you have, that's uh, the 28. So e to the directly is 76 minus 70. That's 6 over 1/6. So k T1 plus 1 is Ln of 0.6. Okay. So here what you have is well, this is k T1 plus k, right? This Ln of, but kt1 is just Ln of like 80 to 12, 12, 28. All right. Here is 6. All right. That's right. Okay. So plus k. So you get where we found this. K is Ln 6. Subtract by Ln. Okay. So this is Ln minus Ln. That is deficient, right? So this is Ln divides by, okay, so I can compute this one. So 6 over 28.6 times 28, 12. That's 2. So that's 28. This is 14. So just say 14 over 28.6. All right, so that's Ln. So that's K. And because 14 is smaller than this one, so this is smaller than 1, so this is negative. So that tells you it's decay. Okay. So now we know the formula for this. So we need to find E1. Okay. And what is T1? Sorry. Do I miss something? Oh, 81. Okay, so we have 70 plus 28.6 to be times and of 14s there. That's the formula. Okay, so then we need to find T when it is, okay. So from the data, T of T1 is is T1 is 82. Okay, so now you can find the T1. Okay, what you get here? So subtract 70, that's 12, right? Divides by 28.6. And you get this is, so E1 L and of 12. Okay, and then you apply Ln. So you get E1 Ln plus Ln of, so T1 is, you can compute this, for Ln 14. Okay, so that's T1. Can you compute the number? That numerator and denominator is equally negative. So this gets you a positive T1.
Sir, I got 1.216.
0.216. Okay, this hour. Okay, so that's T hour after death. Okay, so what time is the time of death is approximate, say, time of death is 10, sorry, the body is found, sorry, let's see, that body is found at 10 p.m. All right, so 10 minus, so that's around, what time is this? In hour is 1 hour. So point two is 1/5. 1/5 is about 13 minutes or so. Okay, 1/5 is 12 minutes. So just minus an hour. 13. So that's approximately about 8, 13, 8, 13, 47. Yeah, time of death. Okay, So that's how we do this a kind of crime scene investigation type of computations. Okay, questions? Questions? So- All right, so this is the few examples of the growth and decay. And we'll continue with the next section. This is linear differential equations. We take a break. Take a break. All right, so then I'll stop the recording now.